Thank you for the introduction, and good day to all of you, ladies and gentlemen. So, what can one do in 10 minutes? According to Swiss timekeeping, one should be able to give a presentation at SMRA, including the questions. But according to Google, you can also do very interesting things as unloading a dishwasher. But would you be able to perform a complete whole-heart coronary MRA exam, including the localizers, the planning, and the actual image reconstruction? Well, that's the topic of this work. So to do that, you would probably like to do some kind of brain-style coronary MRA, or CT as Mark called it earlier, to just place the field of view and start acquiring, irrespective of the cardiac and the respiratory motion state. So in such a manner, you can move away from complicated planning, from navigator gating, and from ECG triggering. So these are all motivations to really go free-running. So as Dr. Botnar outlined earlier, the free-running concept has been a hot research topic in Lausanne for many years now. And as you can see in the schematic of our automated reconstruction framework, there are quite a few steps that pertain to the extraction of physiological motion signals, and moreover, there is a slightly time-consuming iterative reconstruction process. So if you are not immediately interested in the dynamic images, but you are after something static, maybe to see the origins of the coronaries, for example, can we simplify this? Well, that's what we are trying to address here. So, with a free-running acquisition, if you just reconstruct all the acquired data, you will evidently have something that is highly degraded by motion. But it seems natural that we would be able to select just a few of these radial interleaves in order to obtain something that is motion consistent. So this begs the question, how do you achieve such a data selection? Well, for that purpose, we have developed a technique called SIMilarity-Based Angiography, or SIMBA for short. So the idea here is that all the radial interleaves that make up our free-running free radial acquisition, they are stacked in a matrix. So on one axis, you have the SI projections from different coils, ideally the coils that are centrally located at the chest, and then you also have an interleave dimension or time dimension. If we then decompose this matrix with a singular value decomposition, we can extract the principal components and use these to perform clustering with k-means in a low-dimensional space. So the idea here is that we only look at the similarity of the different SI projections. We don't care if they were extracted in some particular part of the cardiac cycle, etc. We just want to know if they are similar. If we thereafter extract the data that was acquired in those interleaves in the largest cluster, we can reconstruct something that hopefully is motion consistent. So in order to validate this technique, in this proof of concept study, we were working with free-running 3D radial scans with an acquisition time of 7 to 8 minutes, 1.1 millimeters isotropic resolution. We had 5 volunteers acquired with a non-contrast, fast-interrupted steady-state sequence, and also 5 pediatric cardiac patients scanned with a gradient echo sequence after administration of ferromoxetol. And these children were respiratory ventilated. So in order to see how SIMBA performed, we just compare it to the motion-degraded reconstructions with all the data, just to get a first sense for if this technique would do something useful. And then we looked at the reconstruction time, the blood myocardium CNR, the blood SNR, and the visibility of the coronary artery segments. So let me start with showing you some examples of what the data can look like. So here you have a motion-corrupted data set with a fast-interrupted steady-state sequence in a volunteer. And then when you apply SIMBA, it clears up quite a bit. If we have a look at one of the pediatric cardiac patients, you can see that when we do the transition to SIMBA, we can start seeing a well-defined myocardium, the papillaries, and also the coronaries. And if we go through the actual slab here transversally, you can see that in the SIMBA reconstruction, it's clear that the right coronary artery comes out of the wrong cusp. So in terms of reconstruction time, just performing a non-uniform fast Fourier transform with all the data takes approximately 30 to 40 seconds on the workstation that we are using. With SIMBA, you can do this much faster. The PCA and the k-means are almost instantaneous, and you also have less data to process in the NUFT and in the for the coil combination. In terms of CNR and SNR, we had slightly improved CNR. We paid a penalty in terms of SNR mainly because we have more noise in the background since we reconstruct less data. When it comes to the visibility of the coronary artery segments, as assessed by a senior researcher, in the non-contrast volunteers, you could essentially not see any coronaries at all. In the SIMBA reconstructions, you could not see all of them, but you could see the majority. And in patients with contrast, you could see more coronaries also in the old data case, but you had a considerable improvement with SIMBA. So what do we actually have in our cluster? So far, we have been reconstructing the largest of them, but if we just traverse the 5 largest, we can see that all of the clusters contain some kind of combination of different respiratory and cardiac motion states. And they all look relatively motion consistent. So now we just traverse them in order of size. So don't try to interpret this as some physiological cine image, because that is not what it is. But if we ask the question, where does the selected data actually come from, that's where it starts to become interesting. So what we saw in most of our subjects was that if you look along the cardiac domain, so here we compare to a motion-resolved 5D XT grasp reconstruction, the majority of the data came from the middle of diastole. But interestingly, we also had some data from immediately after the R wave. And that makes sense since we are working with similarities. They are supposed to be similar, but if you only would bin according to the ECG, that's maybe not how you would do it. And then along the cardiac dimension, we had a preference to end expiratory data. So to get back to what you can do in 10 minutes, we hope that you can do a complete whole heart coronary MRA exam with SIMBA. We are talking 7 to 8 minutes acquisition, less than a minute reconstruction, and then you might need some time for your localizers and for shimming. And this reconstruction technique is completely similarity-based. It doesn't make any a priori assumptions about the physiological processes. So therefore, we hope that it will be robust to arrhythmia and so on. And it might serve as a useful complement to more time-consuming reconstruction algorithms. One can imagine a scenario where you want to do a time-consuming XT grasp reconstruction, but you want to have some image of decent quality to show immediately at the scanner. And there, SIMBA could be an alternative. As a next step, we obviously have to validate this and compare it to reference standard coronary MRA. And as a last thing, I just want to mention that the beauty with a simple technique like this is that even a bad programmer like myself could make it work at the scanner. So we are currently developing this prototype. To conclude, I would like to acknowledge my colleagues in Lausanne and thank all of you for your attention.